Okay, so last class, what did we discuss? Well, I showed you all how a motor works, right? A motor works by having a coil in between a north and a south pole of permanent magnets. Justin, you remember this? And when you run a current through the coil, it creates a magnetic field. Isn't that true?
Yes.
And the and if you create a magnetic field in the middle, and you have permanent magnets here,
Yeah.
so wouldn't the magnetic field over here interact with the other magnetic fields?
Yep.
And that would create thrust. And in last class, we looked at how to do Fleming and apply it to this case, right? Okay, so that's what we did last class, and we also covered DC motors and AC generators. Justin, can a DC motor act as an AC generator?
Yeah.
Okay, how? We had to do with the DC motor to make it generate current,
Um. Well, for the DC motor, it is use a battery, right?
right?
And a AC generator, it is use an external turning force.
Okay, so if I have a motor, what could I do to the motor for it to generate current? Do you remember this?
Yeah, connected to the battery to make it spin.
Connect it to the battery and make it spin.
Yeah.
But if I connect it to the battery, it will spin as a DC motor. But I want to generate current. This is not generating current. I'm supplying power to it and it's spinning. That makes sense. If you want a motor to spin, you hook up a battery to it and it spins. This is not generating power. How? What could I do to the motor for it to generate power? What can you do?
Mhm. Increase the voltage, the battery voltage.
No. Hear what I'm saying, right? We want to generate power. I want you to explain to me, how is this generating power?
Um. Well, the motor is connected to the battery. The battery supplying power to the motor.
Okay, and that is not generating power. What we're doing is we supply in power and that causing it to spin. But what if I wanted it to work the other way around? What if I wanted to generate power? Do you think generating power involves a battery?
Not necessarily.
Max, that question. If you're trying to generate power, why would you supply it with power? Let me explain what I mean by that. In this scenario, you have a battery connected to the motor. So what is causing the motor to spin?
The battery.
Okay, if I remove the battery now, will the motor spin?
No, you have to put your own type of force into it, let it spin.
Okay, cool. And when you spin the motor, what do you think happens here?
Uh, Power is supplied.
Listen,
When you spin the motor, the um
the
power
motor,
is
the motor
pushed
acts as
through
a,
the
what does the motor act as?
as a battery. Well,
Not as a battery, it acting as a generator.
well, yeah.
That's going on. So I'll say it again. If you have a battery hooked up to a motor, you're using it as a fan. You understand that? You sure?
Yeah.
But if I remove the battery, will the motor spin?
No, you have to put your own force into it for the spin.
Right. And if I spin the motor, remember the motor is a coil of wire that's in between two magnets. If I were to if I were to spin the motor, that would generate a what?
Of course.
No. Well, yeah, it would create a force, but what I really want you to say is that it would generate current. It would generate current. So again, Justin, a battery produces current to make the motor spin. It works the other way around. If you spin the motor, it generates current. So in this example, are you seeing a battery?
No.
You're not seeing a battery, but is the LED lighting?
Yes.
So are we generating power?
Yes.
How are we generating power?
By spinning the blades on the fan?
Right, and are you seeing any batteries over here?
No.
That is what it means to generate power. In this example, the battery is generating power, but I don't want to use a battery to generate power. I want to generate power without a battery. To do that, well, you just have to spin the motor and that would create a voltage, right? Did you, and you had this copy down from last class, right?
Yeah.
Did you have the chance to copy this down? These diagrams?
I have the table. I don't have the diagram.
Okay, you gotta copy down the diagram. So before we copy down the diagram, let's just run through this over here. Kirsten, are you able to talk today?
Yes,
Okay, great. So Kirsten, I'm not sure if you did this in school as yet. This is magnetism and induction, right? What I was saying is, if you have a battery hooked up to a motor, the electrical energy gets converted to mechanical energy, right? The battery gives the motor power and it causes the motor to spin. Does that make sense?
yeah,
Now, if I remove the battery, and you agree that it wouldn't spin because it don't have any power going to it.
yeah,
But if I spin the motor, what will the motor generate?
mechanical energy,
Nada, it wouldn't generate that. You given it mechanical energy. So it works in reverse. I give it electrical power, it gives me mechanical. If I supply it with mechanical, it gives me electrical. So if I were to spin the motor, it would generate power. So if I hook up an LED to it and I spin it, the LED would light up. So in this scenario, was the energy transfer? Was the energy was he changed energy here? The battery has what kind of energy?
electrical energy,
And what does it get converted to? Because of the motor.
energy,
What?
mechanical energy,
That's correct. And now if I spin the motor, I'm supplying what kind of energy to it?
electrical energy.
Think about what you're
If
saying. If
spin
you
it is mechanical energy,
right, if you spin something, okay, what you said before, you said if you spin it is electrical energy. Are you a robot?
no, it's mechanical,
Nah, we body don't really have any batteries and thing. We don't work like that. Anytime something is in motion, anytime you're moving something physically, that's so if you supply mechanical, apparently, what we apparently getting out of it, what would cause a
elec
LED to light?
electrical energy,
Correct. So you understand if I so you understand in the first diagram is electrical to mechanical, and in the second one it's mechanical to electrical.
yeah,
Okay, cool. And you would have had this copy done as well, right?
yeah,
Cool. So, Kristen, I want you to read DC motor, and Justin, I would like you to read AC generator. But they work hand in hand, right? An AC generator is simply a DC motor, but you're just spinning it. Because, Kristen, and when you spin a DC motor, you create power.
yeah,
And that's the whole purpose of a generator. And you want to generate power without using a battery.
yeah.
Right. Cool. So Kristen, read the DC motor for me.
The purpose of the DC motor is to create a moment on both sides of the wire, which to create a turning force. This is due to Fleming's left-hand rule, which says that in order to create a force, a current must be perpendicular to the magnetic. When the loop is turning, there is a chance the direction can be reversed every half revolution. A split-ring commutator is used to break the circuit every half turn to keep the motor spinning in one constant direction. The direction of the turning force depends on the orientation of the magnets and direction of the conventional current.
Right. So Kirsten, what we discussed over there was what we looked at in last class. Justin, I see real fixing it here. As usual.
I joined on my laptop, but I don't know how long it will last. So on my phone too.
Okay, cool, good. Right? So Kirsten, you remember me doing this in class?
I think so, yeah.
You think so? I'm asking you a question. Over here we have a permanent magnet or a temporary magnet. What's this?
Um,
It's a block. If you have a bar magnet, do you think a bar magnet is permanent or temporary? If you don't know, tell me or make a guess.
yeah, permanent.
Permanent is a magnet that will always be magnetic. Temporary is something that could stop being magnetic.
Yeah, it is permanent. The bar
Right.
magnet is permanent.
Right. Right. So this permanent and this permanent. Do you remember me saying if you pass a current through a conductor, a magnetic field is generated around it? Do you remember me saying that?
Yeah,
Okay, so this over here, this is a coil. Do you think the coil is a permanent magnet or a temporary magnet?
temporary.
Right, because if I take off power, it's what? Justin, if I turn off the power supply, will this coil have a magnetic field around it?
No.
No, because there's no current passing through. You need current passing through to generate a magnetic field. Kirsten, you understand that, right?
Yes,
Okay, do you remember me showing you left hand rule, Fleming left hand rule?
yeah.
Okay, well, Justin, I can't really put on my camera, so I want you to just explain to Kirsten this really quickly, like just real fast. Um, so first of all, Justin, tell Kirsten, I want you to leave your mic on. Justin, tell Kirsten the direction of the magnetic field. How is the magnetic field going to flow?
Went from right to left.
Right to left?
Okay.
Justin, just lower down the volume in your phone. I'm hearing some feedback, right? Kirsten, do you remember that
Uh,
magnets always go, well, the magnetic field lines always goes from north to south. Do you remember that?
Yeah.
Okay, so the magnetic field lines are going to go from north to south, and we call that magnetic flux. Magnetic flux is the magnetic field lines. So it's north to south. Okay, so that's the magnetic field. The next thing, Kirsten, current. In this coil, we supply and power to it. We have a positive and a negative terminal. Do you remember how conventional current flows?
You
How,
could repeat that, sir?
how does conventional current flow?
Mm, direction of it
Say that again?
means it might be same direction of the positive.
I'm not hearing you properly.
It does flow in the same direction as the positive charge.
So tell me, like negative to positive, positive to negative.
And I opposite. Um,
Wait, I want you to tell me positive to negative or negative to positive. So we have the terminals here, we have the positive side here, and we have the negative side here. How are the charges going to move? Is it going to move?
positive.
Yeah, so positive to negative, right? All right, so Kirsten, pay close attention to this, right? Um, Justin, I want you to
yeah.
explain this side to her. So the current in this side, Kirsten, do you think the current in this side is coming out of the paper or going in? Is it coming out or is it going in? Look at the direction of the current.
Coming out.
It's coming out. So Justin, show her Fleming's left hand rule. So first things first, you pop your left hand. Show her which one is thrust, magnetic field, and current.
Just magnetic field current.
Right. So your thumb is thrust, the second finger is magnetic field, and the last finger is current. So Justin, I want you to align the magnetic field finger from right to left, as you seen on the board. Justin?
Yeah.
Yeah, show us. I want you to demonstrate Fleming's left hand rule. So
Should be
north and
like
south, and the current coming out.
mhm.
Yeah, that is correct. Kirsten, are you confused by that?
No, sir.
Okay, so his thumb represents trust, right? Um, his second finger represents the magnetic field, so it's going from north to south, and the finger that you're not seeing is pointing towards him. Is the um is the current that's coming out of the paper, so it'll be pointing towards you. So Kirsten,
Right.
this part of the coil is going to experience an upwards force or a downwards force.
Downward.
No, they don't understand it. That's okay. You able to put on the camera?
I want more phone so that we kind of hard.
Okay, well, here what you to do. Pop your left hand,
Right.
have your left hand up.
Yeah.
Okay. Your thumb is thrust, your second finger is magnetic field, and your last finger is current. Alright? And it should be looking like this. Right?
Yeah.
So thrust, magnetic field, and this is current.
Yeah.
So the magnetic field is the light blue line that goes from north to south. So you're gonna align that hand in the direction of the arrow, right? And my current in this question is going in or coming out? Is
Coming out.
going in or is coming out?
Coming out.
Right. So that should be going this direction or this direction. Should it
That
be
direction.
should it be going into the screen or away from the screen?
Away.
Right. So that will be pointing towards you, no?
Yeah.
So okay, the magnetic field lines up north to south and the current pointing towards me. So the last finger is thrust or force. Where's that pointing?
Upwards.
Right. So if that is the case, this side of the coil will experience a what kind of force?
Upwards force.
Right. This will experience a upwards force. And this one over here, is the current going in or is the current coming out?
Going in.
Right. So let me do Fleming's left hand rule for that. So same north to south, right? It's going in the same direction, but the current now is going into the paper. So the current going into the paper, magnetic field north to south, and my thumb finger is pointing downwards, right?
Right.
So where's the thrust gonna be? What kind of
Down.
force is it gonna be? Downwards force, right?
Yeah.
Right. So if I have an upwards force here and a downwards force here, would this coil spin?
Yeah.
Yeah, watch. It'll spin.
Yeah.
And what direction is that?
Clockwise.
Yeah, that's clockwise. So that's how it works. That's the principle of a DC motor, right? If there's anything you didn't fully copy down, I'll send the notes at the end of class and you'll fix it up.
Yeah.
Okay, right? So here what let's do. Oh, Justin, I want you to read AC generator real quick. Read AC generator.
AC generator it is noted that instead of a commutator that slip rings are placed at the end of the wire loop. The purpose of these is to allow the transfer of the alternating EMF induced by the rotating wire to the external circuit. Each one of each one is connected to a contact brush where it rotates about the inner diameter. The faster the external
Rotator.
rotator, more electrical energy it can be converted.
Right. So Justin, what we say? We say that. So like, okay, what would I have to do to make the LED shine brighter? What do you think we ought to do?
Spin the fan blades
Slower or faster?
faster.
Right. So here I want to do. I want you guys to. This diagram will be very hard to draw. I don't know how well you're gonna do this. Yeah, how are you gonna do this? That's a question. I doubt I'll be able to draw that. Huh. Here what? Copy down the definition for DC motor and AC generator, and they could try to draw it in our spare time. Right, so I want to let's copy down DC motor and AC generator. Listen, how come you're not on your laptop?
Because my laptop not working.
Oh shucks.
I don't use that. I just usually use my iPad, but it's charging right now, and I'll take her along as I come on my phone. I don't want to leave the class.
Okay, okay, I understand. Thanks for joining anyways. I appreciate that. It sounds like you're feeling better.
Much better today.
That's good. That's good. Right, did everybody have it copied down? Just when I asked that question, did you copy down, is it?
Almost finished.
All right, Kirsten, what about you?
Almost finished.
Okay, good. Well, just remember, I had to scroll down so you could copy down some extra stuff for AC generator. And I would like you all to leave some space in case I will draw the diagram. Yeah. Okay, you all done?
Yeah,
Justin, you finished,
yep.
right? Kirsten, what about you?
Yeah,
Okay, good. Copy this down as well. This is on the AC generator. This is the rest of it.
Finish.
Okay, cool. Kristen, are you done?
Yeah.
All right, cool. Let's move on to electromagnetic induction now. So, Kristen and Justin, I want to hear from the two of you all. If I'm saying that this is a DC motor, right? Kristen, remind me, this over here, this is a what kind of magnet?
Permanent.
Justin, this kind of magnet,
Permanent.
and this one over here. That's really a what?
Temp.
It's a temporary, right? And it's a coil. It's a coil. And we saying that if I spin, okay, so this thing, this part over here, like it will have an attachment over here where you could put in like blades and stuff, right? So, Justin, we were saying that when we spin this, it is do what?
When you spin it,
Mm-hmm. So when we spin
it
the motor,
is fly like energy or power to it.
again, we're not putting any power to it. What does happen when we spin it? Check out the diagram. Check this out. When we spin the motor, what happens?
The bulb just lights.
What is it?
The bulb just lights when you spin the palm blades.
So you're generating what kind of energy?
Electrical.
Right. So Kirsten, when we spin the motor, when we spin this, it generates.
Repeat that, sir.
When we spin the motor, it generates what kind of energy?
We are applying mechanical energy to get electrical energy.
Right. So if I spin this, so let me ask that question, right, Justin? When I spin this, and you could agree that all here have a magnetic field, I have a magnetic field all here.
Yeah,
And when I spin this coil, and this coil is going to turn, and I'm gonna cut through the magnetic fields, you can
yeah,
see it happening because this coil over here is gonna turn, like it's gonna turn, it's gonna turn, right? Kristen,
yeah,
can you visualize that? That it's gonna turn.
Yeah.
So you can see it turning, right? And over here have a magnetic field.
Yeah.
All right. So Justin, this is gonna turn, and if it's turning, ends gonna interact with the magnetic field.
yeah,
Yeah.
Right. And that's what we say in induction is. So we're saying when you pass a magnet along a solenoid, you could create an electron flow and thus produce a voltage. Basically, what I mean is anytime you have a change in magnetic field, it is generate voltage. Justin, you're looking a little confused. Let me say that one more time. So this coil here, anytime I spin that coil, right? Any coil gonna cut the magnetic field.
yeah,
Right, so there's a change in magnetic field because the coil spinning. And if the coil
right,
in this position, it will be different from when the coil in this position.
yeah,
Right. So Kirsten, what we're saying is anytime there's a change in magnetic field, a voltage is produced. And that's how a DC motor does work as a generator as well. Because when you spin it, you're gonna cut the magnetic field at different places. So you would say there's a change in magnetic field, and we call that Faraday's law. Do you understand?
Yeah.
Okay, cool. So I want you all to copy this down. So electromagnetic induction, copy this down. Right, Kirsten, I want you to read it as well. Same, I want you to read this one.
Electromagnetic induction. Passing a magnet along a solenoid can allow electron flow and thus produce a voltage. This is denoted by Faraday's law, which states that the voltage or EMF induced in a coil is proportional to the rate of magnetic force across it.
Right, I'm gonna give only a slightly different definition, right? and put note well by it, NB or something, right? Yes. Justin, you doing anything this carnival? Or?
I'm not sure because my PE teacher he have a lesson Sunday, so I have a cricket Sunday.
Oh, shucks.
So I don't know, my mom and I might carry on somewhere. I don't know because Friday coming we have field trip in school.
Where you guys going?
Well, we pay for field trips since form trip, so they get cancelled. So they're now giving way. We're going Bamboo Cathedral and I think the same Michael Coast Guard.
Okay. You excited or?
Yeah,
Let me guess, you got me fixing it here. Whole ride, eh?
nah,
Yeah, yeah.
nah,
Especially when you reach on these sites.
nah.
Right? So I'm gonna write my definition over here.
I want to leave on a drawing because it's screen black.
You see in the screen black.
Like it had nothing on the screen, like I don't even present them, but I can't see it.
Let me stop sharing shit back. Do that. Hmm. Okay. How about now?
No,
Justin, you see the screen?
Yeah,
Kristen, that's weird. How about now?
nah.
Try leaving and joining back fast.
All right.
we have Papa Susan.
What is it?
Three remember I told you they put me in houses for the sportsy thing, right?
Yeah.
Um, well, they we had a match my house and Mahadev and Alex house Trilochan. They had a football match here in lunchtime, right? And um I see what I've been normal lunchtime when I go outside, I see all the teachers outside. I see Priya, I see Arun, I see Mr. Ganga, I see Ricky, I see all of them there on the field. Them all of them playing cricket, all of them playing football.
Okay.
And well, from lunchtime, I thought it would be a normal lunchtime, like the normal hour we discuss. When I watch the time, I see it's about half one. I said, well, we again back in class. When I asked Ricky said, them playing until school finished. So we missed basically two period of classes.
Probably like yourself.
Yeah. Well, not really because I had physics and English last two period. But Arun, he in charge of Mahadev, so he was playing for the team and all. So
Yeah.
today was really a waste day because we the only class we really had was maths. We correct the Jan paper one for one period and then the next period was free.
Okay.
English B, we didn't have no English B. So basically only one class we had today. I didn't know why I went for.
So like everybody was playing cricket.
Yeah, yeah, everybody was playing cricket and football.
Okay, okay.
Miss Priya, Mr. Arun, Mr. Lakshman, Mr. Satish,
Miss Priya,
Rocky.
since when?
Well, I didn't know because normally she'd just be either in the staff room or walking around up in the by the staff room area, right? So when I see she only feel I say wait now. Something had to be going on. When I go down there I see all the teachers on there.
That was being
I
surprised.
say, well, and she had feeling, she batting, she bowling, she doing all kind of thing.
Hey boy. Oh.
After Punderiki play football too. Punderiki change
Nah.
out her uniform and
Paul Ricky is a man I really like football. He really like football.
like
Right? So
Mr. Rampol, all them play too.
all of them fellas real like cricket and football and thing. Them is real sportsmen.
Yeah.
Real sportsmen. Paul and Ricky, when I was in Shiva Boys and World Cup going on, he pull out his phone watching World Cup right through.
Yeah, he used to do that too. When he in the office too. All the when you pass by the office, all you hear is he woke up with him.
He real love cricket and football. So Kirsten, can you see the screen?
Yeah.
All right. So Kirsten, I want you to read my definition for Faraday's law. So
That's the one on the red right there.
that is your red writing.
Oh, okay.
Oh, yeah, we're
The
talking about this
mag
writing.
yeah.
Okay, well, yeah, let's sing away.
The magnitude of the EMF induced in a circuit is proportional to the rate of change with time of the magnitude flux that cuts across the circuit.
Okay, so do you know what EMF means? Yeah, do you know what EMF means? It means electromotive force
Oh,
and is a fancy word for voltage, right? And it's literally fancy word for voltage. Right, so Kristen, let me run through what we know, right? So we know that a DC motor is just a coil between two permanent magnets, right? We know that. And we're saying if we want to generate electrical energy, you spin the motor, right? You sure you're with me? You like you understand?
yeah,
Okay. And when you spin it, if you want the LED just to shine brighter, you would spin the motor faster or slower.
faster.
Correct. So when you spin it faster, the coil would cut through the magnetic fields faster. That would increase the voltage. And if the voltage is higher, wouldn't the LED shine brighter?
Yeah,
Right. Everything makes sense there. Justin, I hope you copy this down, right? I see you on your phone.
Nah, I have a copy.
Okay, then how come you're on your phone then? Oh, you're not on your phone? Thought you was on your phone. Thought I catch you lacking. I thought I catch you lacking. Right? So I want you to copy down everything that's on your screen here. Yeah. Right. Kirsten, when you talk and thing, I sure just learn a lot more versus like when you're just quiet. But I also understand that sometimes you just can't talk.
yeah,
But you're learning a lot more now that being put into the spotlight. You're shy, and
kind of.
Justin don't bite, or does he? Justin, you just bite over. Nah, he don't bite. He cool. And well, Aliyah real cool as well. Kiara, she kinda eh, sometime-ish. But everybody cool. So, Kristen, I see you at match tomorrow, right?
Yeah,
Cool. 10 to 12.
So it's if you do like add maths, half 10, but then have a class from 8 to 10, and the class does run later sometimes. That's why it's come.
Oh, okay. Which classes are?
Our teacher in school, she does do all sciences.
Okay, okay. I see. All right. Well, noted. All right. So, Justin, you have everything copied down?
Yeah.
Yeah. Up to here.
Yep.
Okay. Kristen, what about you?
Yeah,
All right. I hope I did write this in a different color, yeah? Because this is Faraday's law. That's Faraday's law. Justin, did you write in a different color or at least put a note NB or something by it? Okay, cool. You're feeling hard to unmute that mic, boy. Way. I see you in sign
No.
language. All right, cool. So let me quiz all them. All right, let me quiz all them. Let me just say I have a coil. Mm, As the coil is right now, I just have it sit down. Does it have any power through it?
No.
Does it create any
no,
power? Listen, does it create any power?
no,
For it to create power, it needs to experience a change in magnetic field. Is there any magnets by this coil? Are you see any magnets by this coil?
no,
No, we don't have no magnets. What if I introduce a magnet? What if I put a magnet over here, but I just leave it over there? Or you think you gonna have a do you think an EMF will be induced in the circuit?
no,
Justin Justin say no, Kirsten say no. Both of you say no, right? Everybody say no, right?
yeah.
Kirsten. Okay. And Kirsten, can you tell me why there will be no induced EMF? Why wouldn't there
And
be a
this magnet,
say that again?
because you need two magnets like one on each side.
No, that's not true. This is a simpler example. This is a simpler example, right? Um, Truth be told, you could generate current with one magnet, but you need a change in magnetic field. If I just put down the magnet over here, will the magnetic field ever change or will it always just be there? I'm keeping it over there, I'm not moving. If I just leave it over there, is there a change in magnetic field? Let me just
No,
just draw the magnetic fields for this. Let me just call this north, south. All right. So Kirsten, if I have a magnet over here and I'm not moving it, right? I'm not moving this at all. Is there a change? Is there Let me look at the definition, right? It talks about the rate of change with time of the magnetic flux that cuts across the circuit. If I have it here, and the okay, so the field lines in red, that's the magnetic flux, and it cutting the coils.
Yeah.
Okay, but is it moving? Is it changing?
No.
So will there be a induced EMF? Well, in other
No.
words, will there be a voltage produced?
No.
Justin, what do you think? What if I move it? What do you think? If I move the magnets? Kristen, what do you think?
If you move it, it matters.
Yeah, because look at the field lines, look at the magnetic flux. Is it cutting? Is it is it cutting the coil, and is there a change in magnetic field? Like look at the magnetic fields, right? Um, is it in the same position or is it moving? Is there a change in magnetic field?
Yeah.
If there's a change in magnetic field, then you would have an induced EMF. So Justin, it was wrong. If I move the magnet in the solenoid, it will generate an EMF because there's a change in magnetic field. Justin, I want you to unmute, right? I needed to contribute. So you said no. Tell me why you say no.
No, that the magnets are actually be connected to the coil.
Connected to the coil? I mean connected to the coil. Hmm.
Well, like I thought the bottom piece where I like touch the magnet, but
Like over here? Like
yeah,
like these bottom pieces?
yeah, but
No. Nah. So let me go through the concept again, right? It says passing a magnet along a solenoid can allow electron flow and thus produce a voltage. So what that simply means is if you have a magnet moving close to a wire, it would generate a current. And when you had the coil, and when you had the motor, right? Look at this motor. And when you spin this, and they're gonna cut the magnetic fields here. You have magnetic field lines here. And this is gonna cut it.
yeah,
You sure you understand that? Like 100%? Like you could visualize it. Like when this thing's spinning, it's gonna interact with the magnetic fields here.
yeah,
Okay. So so if I have a coil here, a solenoid, we call this a solenoid, and I have a magnet, and I move it in and out of it. This over here, this is the magnetic flux, or another word, the field lines. Is the position of the field lines changing?
yeah.
Yeah, like okay, it not staying.
Wait,
It go in here, then
yeah,
it here. So is there a change in magnetic field?
yeah,
Yeah, the magnetic field not staying here. It moving all over. And because it's moving, wouldn't it cut the wires in the solenoid? What? And you can see cutting the wires.
yeah.
And if it cuts any wires, if there's a change in magnetic field, then what is produced?
A voltage.
A voltage or electrical energy, right?
Oh,
So let me go through that one more time. And I'll give a little even simpler definition, or I could take this down to um the voltage produced is proportional to the rate of change of magnetic flux. So Kirsten, what I'm saying is once I have a wire, it could be a solenoid, it could be a coil. Once I have that and I move a magnet, because I'm moving the magnet, the position of the magnetic field lines would be changing, and that would cut the coil, and that would create a voltage. That's what I say. So say that back to me.
You could explain it, but
Okay. So, Kirsten, if you have a piece of wire, let me
Yeah.
just say you have a coil. You know what a coil is?
Yeah.
So, a coil is just like a spring. Once you have a magnet and the magnet is moving, okay, why does the magnet have to move? Why does the magnet have to move? If the magnet is staying in one place, is there a change in magnetic flux?
No.
No, the magnetic field lines will just be in one position and they will never change. But if I move it, and they would change position and I would cut the wires.
Yeah.
Imagine our magnets here. The magnets would have its lines and it would cut the coils. And if I move it, it would have a change in magnetic flux. And that would create the voltage. So I'm gonna explain it in terms of the diagrams. So Kirsten over here, and this is a magnet. You see in the south and the north pole.
Yeah.
Okay, Justin, you see in the south and the north pole?
Yeah.
I'm not seeing it.
No, I switch back to my phone. My laptop battery restart.
Okay. So you have the south here and you have the north here. So Justin, in this diagram, what am I doing?
You moving from no, you're going into the solenoid,
So if I go in E into the solenoid, am I staying still or am I pushing it in?
pushing it in.
So will there be a change in magnetic field?
Yes.
Right? Because at one point it will be here, then since you're pushing it, it will be here, then it will be here. Right? There's a change in magnetic field, and that's gonna cut. What are gonna cut?
Cut the
So the magnetic
um
field line is gonna cut the what's this? This is what?
spring, well the solenoid.
That's not a spring. That's a coil of wire. Anytime you wrap up a piece of wire like that, you call it a solenoid or a coil,
Okay.
right? This is how
Yeah.
this is how your speaker coil is being on, in case you don't know. This is how your speaker that's how your voice coil is being a speaker. Exactly like that. And you have a magnet in the middle, right? So Kirsten and Justin, because we're moving it, and you can see that it have a current in the circuit.
Yeah.
Okay. Now there's another rule called Lenz's law. I'm not gonna cover that too much, but basically it says that anytime there's a change in magnetic field, a magnetic an opposing magnetic field will be created to resist the change in magnetic field. It's a bit complicated, but this is what I want to let you take away from it. Justin, you see how you're pushing the magnet in?
Yeah.
You would expect the current to go in this direction, right?
Yep.
But it goes in the other direction. Same thing over here. If you pull out the magnet, you would expect the current to go in this direction, but instead it goes in this direction. Now, if I don't move the magnet and I just keep it there, will there be any induced EMF?
No.
There won't, because there's no what? I want somebody to say there's no what?
No.
So look at the simple definition I gave you all. The voltage produced
No.
is proportional to the rate of change of magnetic flux.
No voltage being applied.
Again, Justin, it do have nothing to do with a battery. Forget about a battery. This has nothing to do with a battery. Nothing. We generating power here. You, if you're generating power, you're not using a battery, right? So let me say it one more time. Justin, can you tell me what this is? What would I call this? That's your what?
The electrical, the magnetic fields.
Right, that's the magnetic field lines, or we call it the magnetic flux.
Yeah.
Right. Cool. Let me make sure I know what this is again. Kristen, what is this? What do we call this? Kirsten, what do we call this?
Could you repeat that? Your audio kind of like so
Okay, Kirsten, what do we call these lines here? What are these lines called?
magnetic flux.
Yes, magnetic flux or magnetic field lines. If I have the magnet stationary, there's no what? There's no change in,
There's a change in the magnetic flux
right?
field.
So in this diagram, there's no change in, so I write it down. There is no change in, there is no change in,
In the magnetic flux,
correct. And Justin, why is there no change in magnetic flux?
Because there's no movement being applied.
Exactly, not moving. But if it was moving, and I'm sure they will happen. I'll give you all the time to draw the diagram, and you had to draw this diagram, you had to be familiar with this. All right. So, Justin, if I have if I okay, so the lines I just want to draw there, those are the magnetic flux lines, right? If I just have my magnet like this, is the magnetic flux changing?
No.
What if I move it now?
Yeah.
Yes, it changed in position. And because it changed in
And
position,
because
I'm hearing some feedback. Okay, not anymore. That's good. So because the magnet is being moved, the flux lines they are also moving, and it's gonna cut the coil, and that's gonna generate the EMF, right? But because it's stationary, there's no change in magnetic flux. So there's no induced EMF. Right. Last situation. Kristen, if we have the okay, my screen went blank. Uh, right. Kristen, if we have the coil and the magnet moving together in the same direction, I'm gonna tell you what that come like. That come like you in a car. Actually, think of an example. Oh yeah, exactly. Kristen, if you in a car, right? And you
right?
could be moving with the car. Like if you're inside a vehicle and you will be moving
Right.
with vehicle.
Yeah,
So is it that you and the vehicle will be moving in separate directions?
no,
No, so ends it come like you stationary in reference to the vehicle?
yeah,
Right. So it's the same situation here. If the coil and the magnet is moving together in the same direction, it come like you is the magnet and you're in the vehicle, which is the solenoid, and you're moving. But because you're inside, there's going to be no change in magnetic flux because it come like it's saying stationary.
right.
So I would like you all to copy down the simple definition as well for Faraday's law. So the voltage produced is proportional to the rate of change of magnetic flux. Let's change that rate of change in magnetic flux. Right? So just copy down that, right? Right under Faraday's law. So the voltage produced is proportional to the rate of change in magnetic flux. Copy that down, and that's the simplest, that's as simple as it gets. Doesn't get much simpler than that.
Finish.
Okay, Kirsten, what about you?
Finish.
Okay, cool. Right? Did you all copy down this piece over here?
Yeah.
Yeah,
All right, nice. Give Ollie some time to draw the diagrams, right? Right, so Justin, I'm gonna write a statement for the first one. In the first one, because the magnet is being moved, there is a there's a what? Because the magnet is being moved,
Is a change in the magnetic flux.
right? Because the magnet is being moved, there is a change in magnetic flux.
It would take me a little while to get accustomed to this topic, but I'll get it.
Yes. And it's the same situation for the other one too. Because the magnet is being moved, there's a change in magnetic flux. Right. So everybody, okay. Trust that everybody will be okay, right? Uh, Justin, I have a question, right? I have a question.
Yeah.
What is the difference between alternating current and direct current?
Or do you want to catch me off guard though?
Well, you need to know this for the next. All of that is part of this one topic. Again, we did that recently.
Well, let me use the notes again, man. I'll define it and I'll give you the answer.
Okay. Well, you should know what direct current is. In direct current, what doesn't change? It's in the name, direct. Direct
Oh,
current.
wait, the direction of the current that doesn't change.
Okay, and alternating current, what happens to the direction of the current?
It changes.
Periodically. That's what you need to see.
Yeah. Okay.
So, what rule would I use if I want to figure out how the magnetic field looks like around the wire? Would I use Fleming's left-hand rule or the right-hand grip rule?
Lemons up and roll.
No. Fleming's left-hand rule is used to figure out the force.
Oh,
I would use the right-hand grip rule. Do you remember the right-hand grip rule?
yeah.
What does your thumb represent?
Currents, right?
Right, current. And the way your fingers curl represents how the magnetic field would look. So the magnetic field can either be clockwise or anti-clockwise, right?
Mm-hmm.
For a direct current, will the direction of the magnetic field ever change?
Wait, but direct? No.
No. So the current will always be rotated in the same direction around the wire, right?
Yep.
For alternating current, though, you think the direction of the magnetic field would stay the same or it would switch?
Now the switch.
It could switch. And if it's switching, is there a change in magnetic flux?
Yep.
Okay, keep that in mind. Listen, keep that in mind as well, right? Listen, you know the difference between alternating current and direct current? Tell me. If you're talking, I'm not hearing you properly.
You can hear me now, sir.
Yeah, I hear you.
Indirect current, like when it's flowing in one specific direction, not alternate, it's like it could reverse like periodically.
Yeah, that's exactly it, right? Now, I would have taught something called the right hand grip rule, and as we would use to figure out how the magnetic field is around a wire that has current passing through it. I'll show you it just now. Yeah, but copy down the diagram and I will explain all of that to you just now. You just focus on the diagram for now. Yeah, focus on that. All right, so Justin, you go send a picture of the drawings in the chat when you finish, right? Let's see what you come up with.
Try some. If it not the best, I try some.
So it had to make sense, right? I remember the last drawing you did do it didn't make sense. If I don't know if you remember what I'm talking about. You did draw something and it didn't make sense.
Yeah.
So in this one, you have a coil like this, right? And it connected to this thing here. Oh, guys, you see this thing over here? We call this a galvanometer. I will put that here. This is called a galvanometer. A galvanometer. What do you think a galvanometer is used for? Kirsten, make a guess. You see in current. What do you think a galvanometer is used to do? You see it like pointing in different directions.
It's used to measure electrical current.
Yeah,
Okay.
yeah. Is used to detect and measure small electrical currents. So like we're using a galvanometer to see if it have a current in the circuit, right? So awesome.
So we had to draw the little red arrows in the middle.
Listen?
We had to draw the little red arrows in the middle.
Yes, because that shows you that the circuit is generating current. Yeah, that's what it
Alright.
shows. So, Right, so Justin and Kirsten, the diagrams are coming along good.
And I'm going to show answer me.
Something so too.
Where's that?
Something so
Something so.
yeah.
Well, Kirsten, I'm expecting good things from you and well, you and Justin, and both of you draw. Well, Kirsten, I don't know what drawing, but like your notes look nice. So I expecting the diagram to look okay.
It's okay, it's not the well.
Okay. Justin, I see you do this thing where you draw a line here. It don't have no line, let me explain. So you have a coil of wire that wrap like this, and you have one end here, and you have the other end here. That's what you have. That's what really going because you gonna do this,
Oh,
but you don't have nothing like that. It's just a coil of wire, right? You have a coil of wire, and if you have a coil of wire, and you gonna have two ends.
yeah,
For them two ends, just it have a galvanometer in the middle. So yeah, fix that. So
okay.
well done, Kristen. You put butterflies on thing? Hey.
It's a bowl.
Okay, it looked like butterflies. I wouldn't even lie. But I can see why I say it. Yeah, I'll send it on the chat. That's how I say it down. Right. Okay, cool. Right, and I want you all to copy down your little notes to the side. Right, so in this first diagram, I would like you all to say because the magnet is being moved, there's a change in magnetic flux. I also want you all to write down the definition of a galvanometer and the symbol for it. And for the ones in the bottom here, I would like you all to say there's no change in magnetic flux because the magnet is not being moved. So I want to see like all them little notes, like all those little notes. Christina, so you wrote no magnetic flux change. You have to write there's no change in magnetic flux
Oh,
to be politically correct. Right, so Justin, just fix up your errors and add in the extra stuff you see in there. Okay, Justin, and I want to make sure you understand what it is you draw, right? I want to make sure you understand what it is you draw. So, Justin, tell me, what is this? Right there,
That is the solenoid.
right? And we have at either ends of it. Wait,
We mean,
so like this is one end and this is another end. We have
oh, well, two connectors.
two loose ends of the wire, right?
Yeah.
What we are actually doing is we are connecting the galvanometer to it. That's what we're doing. That's what way to understand any drawing. I don't want you to just copy down and you don't understand what is the drawing. So watch. In your drawing, this wire over here has to be connected to this, and this wire over here has to be connected to this. Right? Because you just send me back a picture, updated picture with
Okay.
everything that you're supposed to have. Right, Justin, did you complete everything? Did you make the appropriate changes?
Yep.
All right. Kristen, you?
Yeah, send it now.
Okay. So Justin, when we have the galvanometer looking like this, if the galvanometer looking like this, is there any current in the circuit?
No.
Nah. But if it shift like this, how about then?
Yeah.
Right? And it means that the current going in that direction. And if it's like that, current going in that direction. Awesome. Did you guys copy this down? Similarly, an alternating current constantly switches their directions. By doing that, it inherently changes the magnetic field. Therefore, an AC is therefore able to induce voltage across an adjoint coil. All right, so Kirsten, if you didn't already, make sure to copy this down. Similarly, an alternating current switches directions, etc., etc. All right, Kirsten, we good to go?
I just read
I'm not hearing Kirsten properly. Justin,
distracted.
you just checking it?
I just read the last 4 words.
Oh, okay, okay, cool. Justin, you good to go?
Yeah.
All right. All right, guys. Sorry about that. Yeah, you hear me?
Yeah,
Yeah. My there. Right. Right. So, Justin, I have a question, right? Justin, you there?
Yeah.
So, if I have alternating current, that will produce a magnetic field that,
That changes
right. And if you have a change in magnetic field, what is it that you could produce? Or not produce. What can you induce?
the magnetic flux.
No, you could induce an EMF, induce a voltage.
Oh, yeah.
So what we doing here, we're not really creating power, you know. What we doing is like we transferring energy. So we transferring the energy from the magnetic field onto the coil. That's what we're doing. Okay. Kirsten, you ready to move on?
yes,
Okay, cool. I want to explain this a little bit. Let me explain this a little bit. So I'm gonna put on a DC circuit first. So Kirsten, which one is positive and which one is negative? Which end is positive and which end is negative? Kirsten, which one of the terminals is positive and which one is negative? The longer one is positive or the shorter one is positive? Okay, Justin, which one is positive and which one is negative?
Longer one is positive, shorter is negative.
Right. And if this is conventional current, it goes from positive to negative. What I've just drawn here, that's a DC or AC circuit.
Easy.
That's DC. So if we do the right hand grip rule, right? Let me do that, the right hand grip rule. So Justin, we're gonna do the right hand grip rule, right? So the current is going in this direction. This is what I'm gonna do. Wait, this is my left hand, my right hand. This is my right hand, right? Cool. That's your right hand?
Yeah.
Okay. So the current is going upwards, so I point my thumb in the direction and my fingers would curl in this direction. So that is like that's really anti-clockwise, right? Anti-clockwise. So what that means is the magnetic field around the wire would be that would be wait, right? Right. It would be in that direction. Okay, and you understand that no matter where in this circuit, that's how the magnetic field would look like around it, right?
Yeah.
But if we have an alternating circuit, it's a bit different. So now alternating circuit, things are a bit different. 1 minute, the current could be going in this direction, and the next minute, it'll be going in the other direction. Right. And if that is the case, Justin, and the magnetic fields would change direction. So 1 minute they will be going in this direction, and next minute they will be going in the other direction. And
Yeah.
right. So let me just show that in the diagram. So if you do the right hand grip rule, right, that look like it going in anti-clockwise direction. But if I do it for this one over here now, right, that'll be going in the opposite direction. So if you're going in the opposite direction and there's a change in magnetic field,
Yeah.
yeah, there's definitely a change in magnetic field. And this over here, this is the AC circuit. So in a DC circuit, the direction of current is constant, right? So in a DC circuit, the direction of current is constant. And Kirsten, if the direction of current is constant, therefore the direction of the magnetic flux, or the magnetic flux is also constant. You agree?
Yeah.
Because it doesn't change direction. The current is dependent on the magnetic field and vice versa. So if the current doesn't change, nor will the magnetic field or the magnetic flux. So the magnetic flux is also constant. But Kirsten, if we look,
My brother was something really good.
okay, so Justin, in the AC circuit, the direction of the current is, right, the direction of current is alternating periodically in Italian. That it's alternating periodically. Therefore, the magnetic flux is changing. So you can copy down this diagram and do the explanation right underneath this. Kirsten, are you back by chance? Yeah, I think Kirsten is back. Right. So Justin, as soon as I copy this down, we're gonna move on to transformers, right? Gonna move on to transformers.
Finish.
Awesome. Okay, so this over here is just like a small introduction to transformers, right? Small introduction to transformers. So in a transformer, you have a primary coil and you have a secondary coil. Justin, let's try to understand how this thing works. Let me see how the badnesses go. Ah, all right, let me go, let me go. So Justin, what we have, so again, a transformer consists of two coils, right? You have a primary coil and a secondary coil. For it to work, you need alternating current. So Justin, what is this?
That is alternating current. Well, the symbol for alternating current.
And if you have alternating current, the current is switching directions periodically, you understand?
Yes.
And that also means that the what is switching as well. What is also changing?
Magnetic flux.
Right. And if there's a change in magnetic flux, any wire that is nearby, what happens to it?
Um,
Let me look above. Watch. A voltage is produced, right? Or
okay.
you will say an EMF is induced. So the thing to say is that anytime you have a change in magnetic field or a change in magnetic flux, an EMF or voltage is induced. That's all I want you to say. So, so Justin, let me make some notes here. On the primary coil, let me try down a little introduction for a transformer. A transformer is used to either step up or step down voltage. Right? Transformers. Okay, what will do? Wait, don't copy down anything just yet. Give me a second.
Oh, come on. God. What's his name? Nicholas. So come in class again.
Um, he said that the syllabus finished, so and he's doing past papers in school, so he no longer attending lessons. How we say. Yeah.
Right now, I really depended on you because in school I feel Harun like real far from this finish any syllabus.
We just have two subjects, two topics again to finish. Right? So,
We reach lessons and he in school. Like
well, as soon as we finish with the topics, you're gonna start past papers. Intro. Don't worry, I'll make sure you get like a 1 or 2. But you also have to make sure you get a 1 or 2. You have to put in the work. Right, so what exactly is a transformer? A transformer is an electrical device used to either step up, and what step up means is raise the voltage, or step down lower the voltage. Right. Justin, so you think your phone does use 120 volts to run?
Uh, oh,
No,
yes,
no, what?
maybe.
Oh, no, 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 no. Don't say that in public, eh? People go look at you kind of funny. Don't say that. Don't,
Well,
let me ask you a question. You think your remote, you think your remote is running 120 volts?
no,
That's running two 1.5 volt batteries or 3 volts, right? A lot, if you get any memo, a lot of these things do run on 120 volts. So we need some way at dropping the voltage or either raising it. Most of the time to lower the voltage, right? To either 5 volts or 9 volts or something. So that's what we use a transformer. Kirsten, are you back by chance?
Yes, sir.
Okay, nice. So Kirsten, starting transformers here. Next class we'll finish up and start past papers on these topics. So a transformer
Okay.
is an electrical device used to either step up or step down voltage, right? A transformer consists of a primary coil and secondary coil. Instead of coil, sometimes we use the term winding. So you could put that in if all you want. So instead of saying primary coil, you might say winding. Right, both are correct. So a transformer consists of a primary coil and secondary coil. A transformer needs AC current in the primary coil to work. A transformer works on the principle of mutual induction. Kirsten, do you think why? Well, what saying is a transformer had two coils, right? Right next to each other. Do you think why you would need to use alternating current in the first coil? Think you could figure out why?
Um,
Oh, we know about alternating current.
circuit four,
Say that again?
circuit from back and forth.
You get in somewhere. In our alternating current, the direction of the current changes. And because the direction of the current changes, what also changes? There's also a change in
We might affect so.
like perfect. Perfect. So if there's a change in magnetic flux and there's another coil close by, there will be a,
Could you repeat that?
so we have two coils, right? They're right next to each other. So you have the primary coil
All right.
and you have the secondary coil. In
Yeah.
the primary coil, we supplying it with alternating current, right?
Mhm.
Because it's alternating, we'll have a change in magnetic flux, right?
Yeah.
Because there's a change in magnetic flux, what are we going to get at the secondary coil? So we have a change in magnetic field over here, and that's going to cut through this coil. So this coil going to have a, anytime you have a change in magnetic field, you have what being generated or induced.
Exactly. Correct.
Say that again?
Correct.
Current, right? You have an induced current, or you have an induced EMF. Perfect. So anytime you have a change in magnetic field, a voltage is induced. That's what we look at in Faraday's law. So Faraday's law says that if there's a change in magnetic field or magnetic flux, there's an induced voltage is produced in proportion to the change in magnetic flux. So Kirsten, I'm gonna say that one more time. If you change in your magnetic flux, it would induce a voltage in proportion to the change in magnetic flux. Tell me if you're a little confused by that.
I don't think I'm confused. I like read it over like a few more times.
All right, check this out, right? So over here, check over here, right? What did you do to induce a voltage or a current? What did you do to the magnet?
Can you repeat that? You're breaking up.
So what did you do in this situation to induce a voltage or a current? We had to do the magnet,
Move it.
right? And that would have resulted in a change in,
Magnetic flux.
right? And that would have induced the,
The current
right,
flow.
current or the voltage.
um,
You understand that, right?
Yeah.
So let me look at the criterias. You need to have a change in,
Magnetic flux.
induce a,
Current or voltage.
right? Well, both really. So let me look at this situation over here. I'm telling you that for a transformer to work, you need to supply alternating current in the primary coil, and I'm saying you have a coil right next to it. So because it's alternating current, that 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 would create a what? A fixed magnetic field or a change in magnetic field?
Change.
A change in magnetic field. And if it's a change in
Yeah.
magnetic field, there will be change in magnetic flux. You understand?
Yeah.
Justin, if there's change in magnetic flux and I have a coil right next to it, this coil, what is going to be induced in that coil?
Um, wait, could you repeat that question?
Right there. Right. So I have a primary coil here and I have alternating current going to it.
Right?
So because of the alternating current, I creating a magnetic field that is, so alternating current, the current switches, so the magnetic field would,
Change.
right. So I have a what here? I have a, over here I have a, yeah,
Solenoid. Or change in magnetic flux.
right. So I have a change in magnetic field, you can say that. A change in magnetic field. You could say it's a change in magnetic flux. All them things you could say, right? And because you have a change in magnetic flux and you have a coil right next to it, what will be induced? Right? So because of the change in magnetic field, because of it, I'm saying because of the change in magnetic flux, what will happen, Justin? Look at Faraday's law. Anytime you have a change in magnetic flux, what is induced? Look at the original one. The original definition said the rate, well, the magnet. What did the original one say? The long one that I made you all copy.
Um, I had passing a magnet along a solenoid can allow electron flow and thus produce a voltage. This is denoted by Faraday's law, which states that, and after that, I had a definition you give.
Okay, so that definition is what we're going to see. See that definition?
The magnitude of the EMF induced in a circuit is proportional to the rate of charge with time and
No, it's
the
rate of change. Not rate of
magnetic
change.
flux.
Rate of change.
Oh, yeah.
That's change, not charge. Fix that now. You'll be very
Of the
confused.
magnetic flux
Right.
that cuts across the circuit.
So what it's saying is you have a induced EMF. What's EMF? That's a fancy word for what?
Voltage.
Right. EMF is a fancy word for voltage. So because of the change in magnetic flux, you have a induced what?
Voltage.
Voltage, right. Anytime there's a change in magnetic field, a voltage is induced. Because of the change in magnetic flux, a voltage and current is induced. The secondary, right? So give me a second, guys. Yeah, so this will be the last thing you will copy in this class. The next class, we will look at questions. So Justin, let me go over the concept one more time. Remind me, what is Faraday's law?
The magnitude of the EMF induced in a circuit is proportional to the rates of change with the time of the magnet with of the magnetic flux that cuts across the circuit.
That's a lot. That's a lot to remember, right? That's a lot.
Yeah.
So what we're saying is, anytime you have a change in magnetic flux, there's an induced voltage. That's what we're saying. That's all what we're saying. So Justin, if you have a change in magnetic flux, if you have if a change in magnetic field, what can you induce in another coil? You could induce a
Voltage.
right. So you see how we have a change in magnetic field over here and another coil right next to it?
Yeah.
Right. Well, you're gonna have a change in magnetic field here, so you're gonna induce a voltage in a secondary. So that's the principle behind it. So this is the last thing to copy down today. So copy that down, and next class we can look at questions on it.
Diagram to right.
Yeah, this whole thing over here. And you'll get a chance to copy this down. Kirsten, you get a chance to copy this down?
I almost finished, but I take a picture first, so I write it down after class.
Okay, copy it down one time. I don't know when I take pictures and stuff, I don't ever copy it down, being real. So copy it down one time. Do what you had to do one time. So you don't have to be bothered by it after class. After class is to sleep. Or like watch TikTok or something. Or you already have enough homework and thing in school. Or you don't need to be doing extra work when lessons finish. You know what I mean? So finish it now and relax after.
You come in the past and then when we have in school.
I don't know. When is it bazaar?
Well, so far, yeah, and it might be sometime at the next month or the following month after,
Maybe I might come.
because they want to have the pasta and cashew the same day. So,
Okay.
because I think they're doing this sports day thing to raise funds all like that.
Yeah. Right. So Justin, let me go over the concept one more time. Do you think a transformer will work if it have direct current?
Mhm.
If you have direct current, right?
Yeah,
If you supply direct current to the primary coil, will you have a change in magnetic field?
no,
No, so will induction take place?
no,
What you need for induction to take place?
alternating current.
Well, besides alternating current, what's the main thing you need? A what? A what?
Um,
A sure. That's what P.
change in magnetic flux.
Right. You need a change in magnetic field or a change in magnetic flux to induce a current or a voltage. So that's the main thing. And alternating current does that. So, Kirsten, you agree that a transformer wouldn't work with DC current. As a matter of fact, if you use DC current, you could burn up your house. That's all I know. Kirsten, I had to see it. I had to see a diagram. I had to see a diagram.
I'm still doing it, so taking now I got my pencil going halfway break.
Your pencil point break.
Yeah, it halfway break, and I don't know where I sharpen it. So,
Oh God, my partners used to bite the pencil. I don't know how they used to do that.
oh,
I don't recommend biting it though. I don't recommend doing that. Don't recommend that.
on
But
tomorrow I'll struggle with the break points or not.
you should get a push point pencil.
Instead of break, girl,
Maybe get like a 0.7 then. Thicker lead.
because I had real bad luck with any push point. It is just mash up and I tweak it.
Eh, I cannot pointless then. If you know, if you get a bad, if you get.
Yeah.
Just what's up? Is a push point, a pen, push point.
Mechanical pencil.
It's a nice mechanical pencil. What brand is that?
I think it's 0.5.
Okay, nice. Pentel is maybe best mechanical pencils. When I was in the days of drawing, I used to use Pentel. Okay, so let me just have my notes as soon as I finish. So everything I wrote over here is questions that could be asked in the exam. You could ask you, what principle does a transformer work on? Mutual induction. They could ask you, what type of current does a transformer need and why? Alternating current, because alternating current produces a change in magnetic field. All them things. Kirsten, you have any, the phone you have wireless charging?
Yeah.
You know wireless charging is work on this principle, right?
Real?
What's it?
I knew what you said.
I said wireless charging works because of this. Yeah, so
Oh,
yeah, so your wireless charger is a coil and it has a change in magnetic field. And when you put your phone on top of it, your phone has a coil and that induces the current and that charges your phone. That's always work.
so
Um
it depends on breed.
and so break, oh god. Hmm, wait, wait. So where are we going to now? Can draw with your pen?
Yeah, when I finish it, then.
Okay. Yeah, so Kirsten, you could think of any other instance where induction is used.
Can you
Justin.
repeat that?
Okay, so Justin and Kirsten, can you all think of any other instance where induction is used? I'll give you a hint in the kitchen. In the kitchen. Yeah, Justin, you can give me any example of induction in the kitchen. First of all, let me ask you
Um,
this. What kind of stove you have?
uh, a normal stove, but
With gas.
yeah.
Or nah, you wouldn't. So it have induction stoves that I'm showing a picture what I'm talking about. Induction stove. That's the one without any match or anything or any fire or anything.
I see electrical top stove, right?
Yes. How that does work? That does work on induction. So so the big circle is a big coil, and the pot also has a coil in it. And the change in magnetic field transfers a current to the pot and I heat it up. So this is very cool. This is like one of the more useful things in real life. Like you actually use this stuff. Half of the thing on this video, you know, like I use it in real life. Like when you go and use Pythagoras theorem, when you go and use the quadratic formula, we could actually use this. Right? So Justin, you see what I said?
Yeah.
You see like this circle? There's a coil. And those pots have coils as well, and that transfers the energy. So yeah. So listen, I'm Justin. As soon as I finish, just send me all the diagrams and that'll be it for class today. Oh, Justin, that isn't change, is magnetic field. What do you think it should be? You're right, change is magnetic field. What do you think that should be?
Which part?
The arrow pointing to the alternating current. You're right, change is magnetic field.
Oh,
What that should be?
now it becomes it.
Oh, and I see
It
you put an arrow over here. Is this the galvanometer? Where's the galvanometer in this here?
now have an arrow points in there too.
This is the galvanometer, not over here. I see a point like that.
Now have an arrow going from the galvanometer to the node.
Right, but also see a sensitive galvanometer is necessary and you draw arrow like this is what he was talking about. That note, the
Oh,
sensitive
no.
galvanometer,
That was a mistake.
the sensitive galvanometer should like be under this. I know it's over here, but you should probably put it over here. It'll make more sense, right? Now, Justin, because it's alternating current, it will change directions. So the galvanometer will be pointing in this direction 1 minute and that direction the other minute. Cool. Listen, you can send me a picture what you have.
I send it now.
Okay, good.
We're not judging because we have to even know draw it there.
Okay, we're not judging. We're not judging. I don't even know what judging is. Let me see what you have here. Okay, you draw those coils way too far apart. I wouldn't work if it's that far apart.
So that'll be
Yeah, the coils have to be very close together, like exactly how you see it in the diagram.
all right.
And did you copy down this? I'm not seeing this.
Half of the second point. All right, so here's.
Okay, well, I was sending notes, but I'll be it for class today. Right? Thank you all for coming to class. Next session, we're going to be doing calculations and past papers. Right? Before we move on to logic gates. So yeah, guys, as that was it for our whole topic, more or less. The only two topics we gotta do next is logic gates and the atomic part of physics, radioactive part. So yeah, guys, have a good night. Later, everybody.
Bye.
Bye.